So as we've already seen, a free scalar field can be described by the Lagrangian such that L is equal to the volume integral over a real space x times script L, where it's minus 1/2 m squared phi squared. Now, our goal is to quantize this theory in the sense of developing a quantum theory that... I have no idea what I'm saying. That's the first thing. I know what I'm saying, obviously. I know the words, and I know the equations that I'm supposed to write, but I have no idea what any of it means.
Als je als docent voor een klas staat, gaat het er vooral om hoe je lesgeeft en niet om wat. Om dat uit te beelden leerde de Amerikaanse theatermaker Billy Mullaney voor zijn voorstelling Semester een bestaand college over kwantumfysica uit zijn hoofd en kan hij als een volwaardig professor lesgeven, terwijl hij er zelf helemaal niets van begrijpt.
That's the first thing that I would tell the audience. Like, and no one would come not knowing that, like, hey, the concept of this performance is that I have memorized this physics lecture, that I don't know what it means. You're not expected to know what it means, so then, now what? So I mentioned this is choreographic. Okay. So I have a choreography across the board, and I can space it to whatever amount. So this is 120 divided by 4 is 30.
So you do know math?
Just enough to be able to fake it, yeah? It's important to me as well that everyone does know that I don't know. As opposed to say, hey, we can go to a lecture by a physicist, you know, who knows? And then we would sit there and we wouldn't understand. But I think it's important that we all sit together and be like, yeah, no one in this room understands this, even though it's supposedly the fabric of space-time, you know? I might need a bit of time to fill in maybe the first 3/4 of the lecture, because it's most impressive when there's a whole lot of equations and then it's like, oh, and then, you know, as we've already said, da-da-da-da-da. So I'll be performing the end of it. I think that's a bit of what I'm getting at with this. It's less about what is being communicated when we get rid of all the language or the things that you're supposed to understand in a lecture situation. And then it's just about how it's performed, you know? How is knowledge performed or how is expertise performed? As long as I, you know, then it sounds right, you know? It kind of looks right.
Semester Lecture 1.
So we view phi of the position vector x and t as a collection of dynamical variables in the classical theory that we have promoted to operators in the quantum theory, exactly as we did with the discrete systems in section 1. We can now use the Fourier transform to define convenient linear combinations of these operators, such that phi twiddle of vector k and t is defined as the volume integral over a real space x times e to the minus I vector k dot vector x. It took a year of repeating it, kind of like when I was washing my dishes and be like, okay, phi of the position vector x and t is equal to 1/4 of what, you know. But I found that, hey, if I connect it to even some movement, you know, of my wrist, that I can hook it to, and also it's not random. Pi twiddle we will define as, pi twiddle of vector k and t, we will define as the volume integral over a real space x times e to the minus I vector k dot vector x times pi. There are some recurring characters, and I maybe I've been with them for so long that it's like, oh, here comes k, you know, or oh, x is back again, and q dot, not q, you know, this is like an imposter. So yeah, so I can add value or meaning to it, even though I don't necessarily know what it means per se. Now, the fact that phi of the position vector x and t is a real classical variable and hence a Hermitian quantum operator implies that phi twiddle of minus vector k and t is equal to phi dagger of vector k and t, with a similar relation for pi of vector k and t. I feel like when I've performed it, there have been some people who are impressed by the virtuosity of just memorizing the text and being able to deliver it. That's cool, if that's what they're into. Some people very much hook into, and in a not entirely positive way, like, what do you think you're doing? What does this mean about teaching? Or what does this mean about learning? You know, I'm effectively proposing, like, you don't ever have to know anything, or we maybe never know anything. To test this hypothesis, we can compute the commutator of phi sub 1 of vector k, and phi sub 1 of vector q. So using equation 53 and the canonical commutation relations, the commutator of phi sub 1 of vector k and phi sub 1 of vector q is equal to 1/4 the volume integral in a real space x, volume integral in a real space y times e to the minus I times the quantity vector k dot vector x minus omega sub kt times e to the minus I times the quantity. I feel like it's as interesting to be like, how can you teach someone something if you don't yourself know it? Which I think is about being like, okay, well, I mean, we could take a look at the board and we could be like, well, there's an X and now there's an X. Okay, I recognize that. And then we can slowly parse together maybe how it's constructed and ascribe some value to things. So we can learn at it, even if we don't learn it. We can now use the identity that the volume integral over a real space x times e to the minus I vector k plus vector q dot vector x is equal to 2 pi cubed times the delta function of vector k minus vector q, which implies that the only possible non-zero contribution to equation 54 arises when vector q is equal to minus vector k, in which case the factor in curly brackets vanishes. Thus, the commutator of phi sub 1 of vector k and phi sub 1 of vector q is equal to 0, as we would expect if phi sub 1 of vector k was proportional to an annihilation operator.